Happy to introduce Robert Kropholler from Tufts University, who will talk about hyperbolic groups and their subgroups.
So, thank you very much for inviting me, and thank you all for coming. I found out that these talks are live streamed, so you could be watching this from the comfort of your bed. But so I'm even more impressed that you're here. So thank you. Okay, so what I want to talk about today is some past work and sort of a program for the future. And this is going to be sort of an advertisement. I mean, all talks are an advertisement. This is sort of an advertisement of we have a technique and we'd like to find some more applications. So if you can think of anything while I'm talking, please make a note or just shout it at me. Either works. Okay, so what was the question that I wanted to work out? So let's start with the definition. So probably most of you are familiar with the following, but we say that a group is type Fn if it has a classifying space with finite n skeleton. Okay, so parts of this definition, so if you haven't seen this before, the thing that you should think of is that this is sort of trying to take the sort of usual finiteness conditions you're familiar with to a step further. So F1 is equivalent to finitely generated, and F2 is equivalent to finitely presented. Okay, so somehow you can think of them as just higher dimensional versions of finite generation and finite presentation. Okay, and the question that I wanted to work on, or that sort of motivated me to getting into this, was a question of Noel Brady, which was do there exist groups of type Fn not Fn plus 1, so they satisfy some finiteness property but not the next one up, with no C squared subgroups. Okay, so I should pause for a minute and say, you know, maybe if you're looking at this, it's not maybe immediately obvious that groups of type Fn not Fn plus 1 even exist for all n. And I'll give you some examples in low n, but for examples in all n, there's the work of Bespina and Brady on right-angled arting groups, and what are now known as Bespina-Brady groups. So he asked this question, and seeing this question, knowing that I know that you can find groups of this type as subgroups of rags, I thought, well, which groups are going to satisfy this property? And so my first thought was, well, you know, one class of groups which don't have z-squared subgroups is hyperbolic groups. So let's try and find these things as subgroups of hyperbolic groups. So there we go, hence the title. And so I should say that that may not be the best way to go about it. So, so let's give some examples. So, so for F0 not F1, well, F0 is an empty condition, so this is actually just subgroup which is not finitely generated. So let's take an infinite index normal subgroup of a free group. Okay, so we're probably all familiar with this, right? This is a not finitely generated subgroup, so it's F0, not F1. All right, so then we look for a slightly harder example. So look for F1, not F2. Okay, and so the first construction of such a group, I guess, is due to it's a theorem of Rips. So so how are we going to get such a group sitting inside a hyperbolic group? So yeah, maybe I should just write here that. So we're going to look at finding examples as subgroups of hyperbolic groups. Okay, so that's the program that I want to talk about today. Okay, so F1, not F2 is saying something finitely generated, not finitely presented. Okay, so the easiest way I know of doing this, and there are many other ways, and there are. Well, let's just write the theorem. So given finitely presented Q, there exists a hyperbolic group G and a map from G onto Q with finitely generated kernel. Okay, and I've written Rips, there are many forms of this construction. And furthermore, if Q is infinite, finitely generated kernel, say n, n is not finitely presented. Okay, so this is one way to construct lots of these examples, right? So take your favorite infinite group, Rips' theorem from 82 will tell you how to construct a hyperbolic group and a surjection, and the kernel is finitely generated and not finitely presented. Okay? And so after this, the next thing was F2, not F3. Okay, so there do exist examples like this, and they're slightly more involved, and I'm going to discuss one of them. So this is theorem due to Brady. So Brady in 99 gave such an example. Yash Loda in 2014 gave an example, and for anyone who's seen me talk about this before, that 17 used to be a 16, but hasn't arrived yet, so gave an infinite family. So there exist infinitely many pairwise non-isomorphic hyperbolic groups, each containing a subgroup of type F2, not F3. And here's my first advertisement for something that I'd like to do and I'd like to have any input on. So this non-isomorphic is not actually strong in the way that I proved it. It's actually, this is kind of a weak statement, right? So I have these infinitely many groups, but it is possible that they're all commensurable. And so the next thing I'd really like to show that there are infinitely many commensurability classes. Yeah, I mean, I guess I'm saying that, yeah, right, so I guess this is the statement I want. I'm not being very precise in the statement. I mean, the point is that pairwise non-isomorphic hyperbolic groups. I mean, okay, so the reason that you don't get, what you're saying is that each of these subgroups is the kernel of a map to Z. So, right, so, yeah, you're right. So this is what I'm saying. There are many ways that you could get this infinitely many theorem by doing some silly things. And you don't do that silly thing, but maybe you did a different silly thing and you got this theorem. But I think the construction is in fact more robust than that. Okay, so I want to talk about, there's sort of two constructions hidden in this theorem, and there's obviously a lot of other stuff hidden in this theorem. And I want to sort of give a flavor for one of them. So to do that, I would like to define, so make sure I get this right. Okay, so firstly, notation. So if we have a flag complex gamma, does anyone want me? Yeah.
I think I remember vaguely, if you take an arithmetic group in SL3 over function field, simply, they were F, no, okay, SLN over function field, they were F something and F plus N and not Fn plus 1, or under theorems like that?
Yeah, well, I've lots of z-squared subgroups, though.
What?
Your group's got lots of z-squared subgroups.
Ah, that's part of the game. Yeah, you don't want to have it.
Yeah. So my game is that I want to find them sitting inside hyperbolic groups.
Okay, that's why you want them.
Yeah, somebody once said to me that this is a very masochistic game to play because, you know, we all know that hyperbolic groups are lovely, and my game is like saying, well, let's look really closely at them and maybe there's some horrible stuff inside. So anyway. Oh, okay. Sorry. So I should pause for a second before I like fly into the construction of this. This is genuinely all that's known, right? So you might look at this and you might think, well, surely we can do Fn, not Fn plus 1 full n. But we're actually stuck. F3, not F4, is still completely unknown to us. And in fact, I should mention. Did I hide the erasers? Yeah, cunning. I should mention here. So. Fn not Fn plus 1 is, you know, it's a very big question mark. That's a big open question, and I'm going to talk a bit more about trying to do this later. I should also mention some results in the other direction. So there's a theorem of Gersten which says that if G has cohomological dimension 2, is hyperbolic, and N is a subgroup of G, then N finitely presented implies N is in fact hyperbolic. Okay, so if you're in the correct dimension, you know, it is actually true that every subgroup is hyperbolic. So it could very well be the case that if you have a hyperbolic group and a type F3 subgroup, then it is hyperbolic. Although I suspect not. All right, so moving on to an actual careful statement. So if gamma is a flag complex, and X is a subset of the vertices of gamma, then, so yeah, this was the notation that I was going to write. Gamma X is the full subcomplex on X. Okay, so that'll be useful. So, to sort of give you some flavor of what goes into part of this theorem, we have the following definition. So, a graph gamma is sizable if, well, 1, gamma is bipartite, on A and B, and these things split as disjoint subsets with a plus and minus. Okay, so this is just, so far I've just said it's a bipartite graph. I haven't said anything about this splitting. 2, gamma has no 4 cycles. Okay? So, well, okay, so there are no induced squares inside gamma. And finally, gamma on AS union BT is connected for all S and T in plus minus. Okay, and somehow I'm going to use this. This is going to be the input to the theorem. So the actual statement of my theorem is, oh, yeah, okay. So the actual statement of my theorem is, given gamma 1, gamma 2, gamma 3 sizable, there exists a non-positively curved cube complex X, which is going to be, which obviously depends, well, not obviously, but does depend on these 3 things, which sits inside the product of AI joined BI plus 1. So this is, oh yeah, always forget. Sizable, gamma I is contained in AI join BI. So this is once again just saying that it's complete bipartite. This is just saying that the vertex set of this is AI union BI. Okay, so this is just saying that it's contained in a product of 3 bipartite graphs. Exists this such that pi 1 x is hyperbolic, and let's call this G, and G maps onto Z with F2 not F3 kernel. Okay, so for those of you who are familiar with cube complexes, you're probably now, or maybe, yeah, if you're familiar with cube complexes and Morse theory, you might be looking at this and sort of being able to guess how this is going to come about. So I don't want to tell you what this subcomplex is. If you really want to know, find me, but it's just a sort of horrible technical, you just say which vertices are in and then take the full cubical complex on those vertices. And it's not pretty. Okay, but the point is that somehow condition 1 from sizable is giving us the map to Z. Okay? If you've seen right-angled arting groups and you've seen the sphericalization of a flag complex, you sort of have this natural plus-minus structure there, which is somehow telling you how you're going to map to Z. Condition 2 is what's used to prove. So how are these graphs going to come into play? Well, to prove X is hyperbolic. Okay, so these graphs are going to be the links of edges in a cube complex. Okay, and now, so these are going to be the links of, we're going to have a three-dimensional cube complex, and the links of these edges are going to be gamma 1, gamma 2, and gamma 3 respectively. And the fact that they're 5 large is what we're going to use to prove that this thing is hyperbolic. Okay? So say if you're familiar with cube complexes, no 4 cycles is a very common condition in proving that things are hyperbolic. And 3 is what we're going to use to show the kernel is F2. And it turns out that we get to the fact that the kernel's... So the hard part is actually proving that the kernel's finitely presented. Proving that it's not F3 you actually sort of get for free when you run through this program. So I don't want to tell you what the program is too much, but basically you're going to put orientations on these graphs which give you a map to S1. That's going to give you a map on fundamental groups, and then we're going to look at the kernel of that. Okay, so that's a flavor. And I should say at this point that right, so having just written down a definition, there's no reason that these graphs should exist. But I should say at this point that it's thanks to Giles, who helped me very kindly by running some computer simulations to find small examples of these graphs. So they do exist, and we've managed to find what I believe is possibly the smallest one, but I think Giles thinks there might be a smaller one to use that.
How big is it?
The one we have has 36 vertices.
Or 31.
Or 31. 31, there you go. Depending on the structure?
Arithmetical.
Oh, right, yeah, so 31. So they're also kind of big. Yeah. Yeah, and sadly, when you start figuring out what these conditions mean, you realize that they sort of have to have a minimum size of about 20-something vertices. 4 times as many edges. Okay, so that's sort of, that's what I've done, and that's, the reason that I wanted to put this theorem up in full is because we're going to see how I'm trying to sort of get somewhere with it later. And possibly later I'll talk a bit more about step 2 in this proof, which I think is, maybe we'll see something. So, okay, so great, we've done up to F2, not F3. What's really stopping us, let's inflate that differently. So what is really stopping us going forward? Why can't we just run some machine now which is going to throw out the other examples? Well, here's an observation. If a group is type Fn not Fn plus 1, okay, so what does this mean? It has a classifying space with finite n skeleton, but infinite n plus 1 skeleton. Okay, well, one thing that means is it better have an n plus 1 skeleton. The empty set is finite, I think is what I'm saying. So if it's type Fn not Fn plus 1, then the geometric dimension of G is greater than or equal to n plus 1. Okay? It needs to have at least that dimension. If we could find an n-dimensional classifying space, then we'd be able to find a finite one. Okay, and since geometric dimension is inherited by subgroups, we need hyperbolic groups with high, I guess I'm going to say geometric here. Okay, but if you're happier, think cohomological dimension. Almost equivalent. Right, so we need hyperbolic groups of high geometric or cohomological dimension. Okay? And that's really one of our issues. There aren't that many of these around. So what are the previous examples? Well, there was a conjecture of Gromov which said that if a hyperbolic group had high enough cohomological dimension, then it contained an arithmetic lattice of finite index. Somebody can tell me if that's the wrong statement. No?
Not finite.
Oh, not finite, but it contained a lattice. Oh,
Yeah.
it contains a lattice. Yeah, you're right. Free products of things would be bad. Okay, yeah, so, I mean, it's not right, it's not true. So, there are several examples. Several examples. So the first, there are several examples. So firstly, due to, let's spell this correctly, Januszkiewicz, Kwiatkowski, who gave some examples in '03 and some more in '06. There are also some examples by Haglund in '03 and some more examples by, seeing as I've been talking faster than I was, I can take the time to write this out. So Argensaver, Bridson, Januszkiewicz, Leary, Minyazhin.
Sure you have time?
Yeah, I was like, I'm talking faster than I practice, so I can just really, yeah. Kwiatkowski. Okay, in '09. Okay, so there were some examples there, but
The question is, what's the precise statement? What do they not contain?
so these don't contain lattices, I believe.
Why does containing a lattice smash you up? Why are they not?
It doesn't. I just wanted to say that we didn't have many examples. Maybe I shouldn't have said that. Maybe that was something that I shouldn't have said. Maybe I should have glossed over that.
Well, it always contains a circle.
Right. Yeah.
So, what about
But that would be fine.
But I think
I
it's
don't know.
two different questions.
Yeah, there are several different questions. These are the answers to what?
These ones don't contain
Hyperbolic
lattice.
that dimension which are not.
Or maybe I should look into the audience. That's true, right? Good. Okay. These don't contain lattices. Look to one of the authors of said paper. But these aren't. But it turns out that these are bad from my perspective, because what are all these constructions? Well, so all these constructions produce systolic groups. So I'm not an expert in systolic groups. These two people are here. This one's arriving tomorrow night. So, searching out. Okay, so these all produce systolic groups. However, it's a theorem due to, so I think Wise did the torsion-free case, and later the general case was done by Gaspar Sadnik. So if N is a subgroup of G, G is systolic, N finitely presented, then N is systolic. So this is something like the Gersten theorem I wrote up earlier. Systolic groups are stable when you pass to finitely presented subgroups, right? So I'm certainly not going to be able to find my F3, not F4 examples in here. Okay.
What is systolic?
Sorry.
What is systolic?
So systolic is some form of combinatorial non-positive curvature. So you don't have genuine non-positive curvature, but it's the thing like you take a simplicial complex and the link of every vertex has no cycles of length less than 6.
And how does this interfere with your problem?
Oh, so I should say that I guess that this implies n is Fn for all n. I guess I didn't say that. So the moment I have finitely presented, I have Fn for all n. So I'm kind of sad, but I hope should not be lost. Wow, I really am talking much faster. So there's another construction due to Damien Sider in 2010. So there exist right-angled Coxeter groups of so there exists hyperbolic right-angled Coxeter groups of arbitrary cohomological dimension.
Virtual.
Virtual. Sorry. Yeah.
Yeah, I was going to say.
Yeah.
Wait a minute.
Yeah. They have commutator subgroups of arbitrary cohomological dimension. Okay, so and how are these constructed? Well, the way to construct these is to use an inductive construction. So the first question is, when is a right-angled Coxeter group hyperbolic? And we saw this in the last talk. So
How convenient.
I know, but let me remind you all. It's not when I'm talking this quickly. So, so a right-angled Coxeter group, say WL. So the right-angled Coxeter group on the flag complex L is hyperbolic. Hyperbolic if L is 5 large, or this was called in the previous talk square free. Okay, so this means that so this is that anytime we see a square sitting inside L, in fact we see one of the two chords. Okay, so how did yeah, and the second thing is how do we know how we're going to get the arbitrary cohomological dimension? Well, I guess I should apologize. These two should have attributions that I forgot to write down. Bad. Bad of me. Okay, so if the nth homology of L is non-trivial, then the cohomological dimension of WL is at least n plus 1. Right? So, to put into this theorem, what we really need to do is we really need to find examples of 5 large flag complexes with non-trivial nth homology for every n. Okay, and the way this is done in this theorem is you start with something. You start with a 5 large guy. You build the associated right-angled Coxeter group. You then take the Davis complex and take a sufficiently high enough finite index cover so that when you thicken that, you get something that's 5 large, and the inductive step is showing that this homology jumps up another degree. So this homology is going to jump up, then you put this new L that you got back in, you're going to get something else out. Right? So these things exist, but they're not immediately easy to put their hands on, in part because when you run a stage of this construction, if you start with the dimension of L equals K, say, you build WL, the Davis complex has dimension K plus 1, and when you thicken it, you now have a simplicial complex of dimension 2 to the K plus 1. So the dimension of these simplicial complexes skyrockets, whereas the dimension of the homology is sort of staying fairly close. Right. Another issue is this. So this is what I wanted to talk about. So so 5 large is a tricky property to satisfy. Right? I mean, if we had an abundance of 5 large complexes, then maybe this whole thing would be much easier. And it's known that no triangulation of a 5 manifold. Guess I should throw the word. No triangulation of a 5 manifold is 5 large. Right? So, or in fact, and this will tell you that no triangulation of an n manifold for n greater than 5 is 5 large. Right? So, finding 5 large complexes really does place a lot of restriction on what you're going to find. So, so somehow, looking at this and trying to apply this, right? So, looking at this construction and trying to apply some sort of Morse theory is a tricky thing, because somehow Morse theory is these ascending and descending links are very delicate, and somehow just throwing in an extra edge or an extra vertex really completely messes everything up. For instance, if you just remove the connected assumption in sizable, then this thing immediately drops to very rarely being even finitely generated. So somehow, it's actually there's a delicate procedure, and you just kick something slightly, everything falls apart. Okay, so 5 large is a tricky thing to find, and we want to do some delicate procedure. So what I wanted to do was try and relax 5 large. I shouldn't have erased this. Oh well. Oh, and I should yeah. I guess I should have paused and said, and given some sort of implication of, I mean, so this isn't that hard to, the way that you can prove this is if you take a cube complex, all of whose links are 5 large, then what you can do is you can replace every cube with a small cube in hyperbolic space of the correct dimension, and you'll find that this 5 largeness will tell you that your links are still cat 1. So in fact, if all your links are 5 large, then your space supports a cat -1 metric, which in particular is going to give you hyperbolic. And somehow that's a sort of the easy way to prove that cube complexes have hyperbolic fundamental group. So we sort of I wanted to relax 5 large because I'm hoping that this will find it easy. So to that end, yeah, so how can we relax this? So definitions. So a pair of flag complexes A, B, yeah, right. So here I'm going to write n-partite. I'm going to give you the definition of n-partite in a minute. So a pair of flag complexes A and B are, a pair of n-partite flag complexes A and B are, what did we decide? Pairwise 5 large. If, well, I should put in brackets over here. So A is n-partite if A is contained in a join of discrete sets. AI discrete. Right, so 2-partite is the same as bipartite graph. So just sort of, I'm just doing that. So, so they're pairwise 5 large if every 4 cycle in A or B is contained in in A of AI union AJ or B of BI union BJ for some IJ. So I guess the way I like to think of this is that saying it's n-partite is like saying the underlying graph has an n coloring. This is just an n coloring on your graph. Okay, none of the point of it being a join is that nothing in A1 is adjacent to anything else in A1. And so this is saying that if I see a square, then I can color the vertices with 2 colors. Okay, and 2, for each I, J in 1 up to n. So for every 2 distinct integers, I and j, n, either B on BI union BJ or A on AI union AJ has no force cycle. So these last two things I've written down are just bipartite graphs, and I'm just saying that they have no force cycle. Okay, and then great. Right. So once again, these flag complexes that I'm describing here, they're going to be taken as input, and they're going to be something like the links. In this case, they're going to be the links of vertices. Okay. So the following theorem. So this is myself and Federico Vigolo. If A, comma B are pairwise 5 large, there exists X, which depends on these things, which is once again sitting inside a product of complete bipartite graphs, if we want to n, such that pi 1 x is hyperbolic. Okay, so this statement is kind of weak, but I guess I want to be kind of careful about saying things that's false, because some of this is work in progress. Right, so examples, or one example that I really should mention is that if A is some flag complex, is just some flag complex, and each AI is just one point, right? So this is just the laziest possible way you could color the vertices of A, and B is a join of S naughts is a join of the appropriate number of S naughts, then pi 1 of x a b is equal to the commutator subgroup of the associated right-angled Artin group, right-angled Coxeter group. Right, so we can take, we can output that, but then also we can relax things. And I should say at this point that, so Federico and myself would like to use this to find subgroups of hyperbolic groups. And that's still work in progress. As I said, this is an advertisement. So if anyone has any other applications in mind where they want sort of concrete examples of high-dimensional hyperbolic groups, I'd be very interested to hear your thoughts, and Federico would also be interested to hear your thoughts, and he's around for the full semester. Okay, so a quick word about the proof. Maybe I can say a long word about the proof. So, how are we going to prove this theorem? Well, as I said, these complexes A and B are going to be the links of vertices. And in fact, a sort of way to tell you what this complex is without going into the details is if you just take a cube of the appropriate dimension, let's say 3. My drawing skills aren't that great. We essentially create the complex which has link which has link A in one vertex and link B in the opposite vertex. That's really what this cube complex is. And okay, so to prove hyperbolicity. Okay, and this is is a key technique. So, the M-parside structure on A and B, together with the way this is constructed, gives a map from X into a product of n trees. Okay, and now that I know this notation, I can just do that, right? Let's look for the person who made this notation. Okay, so this is an L1 embedding. There's an L1 embedding of this cube complex into a product of n trees. And the idea is you just consider hyperplanes dual to, you color the edges and color the hyperplanes by which edges they're dual to, and then this is known to give you a map to a product of trees. But the key thing is that, oh, right. Sorry, I missed out a key theorem. But I'm sure you all know it, so it's fine. So, I almost got through a whole talk without mentioning Martin Bridson, which is usually not done by me. So, it's a theorem of Bridson which says that X cat 0, well, say X compact non-positively curved has hyperbolic fundamental group even only if there does not exist I from a Euclidean flat into X tilde isometrically. So the only obstruction to being hyperbolic is that you have a full flat plane. Right, so we're going to try and rule out full flat planes. That's what we're going to try and do. Great. Okay, so we have this embedding into this product of trees. And from this embedding, we're going to look at what happens to, let's assume we had a flat in our cube complex. So, assume, say, E squared embeds into X twiddle. Okay, so this is my isometric embedding, which I'm going to call I. Okay, oh, God damn it. Okay, I'm doing the bad thing where I don't distinguish between universal covers, so this should be X tilde. Right? The cat 0, this is a compact space, and the cat 0 universal cover has an embedding into a product of trees. An L1 isometric. Okay, this guy embeds into a product of trees, and if we project down to a single tree, then the image of this, so let's call this map Fj, so the image of Fj is contained in a line. Okay? In fact, we can even do slightly better than that. We can embed this into its cubical neighborhood and there's a map from the cubical neighborhood to Tj. The image of this cubical neighborhood is contained in a line. Okay, so what we're going to do is pick a point X belonging to I of E squared. So let's look at Fj fj bar of x. Horrible abuse of notation. So this is in Tj. So there exists a map from Tj to R, which is cubical and injective on the image of fj bar. And the easiest way to define this map is just to take the edge which contains this point, send that to some edge of R, and then send everything else just away from that. So you're sort of just, your map is basically distance from this point in a positive or negative direction in the half space. So the neighborhood of E squared actually embeds into R to the n, right? So before we were trying to look at a flat plane in some arbitrary cube complex. Well, this is tricky, but looking at flats in R to the n is much easier. Okay, and in fact, so everything I've said so far I haven't really used any of the hypothesis of the theorem. This is true general with hypothesis of theorem. This is an L2 embedding. L2 embedding. So maybe L1 flat planes can look slightly weird. They can bend and kink in ways that maybe you don't immediately think about. But L2 flat planes, they're just you know, flat. Okay, and so finally the sort of next key thing, I guess I'll just say quickly, is an examination of, right, so, God damn it. So this, I've just cunningly erased. So my point so the second point in this definition was that for all n choose 2 choices of these subgraphs, one of them had no 4 cycles. And so what that corresponds to here is it's giving us some codimension 2 subspaces of Rn, which this flat can't intersect transversely. Okay? And so the remainder of the proof is to show that you would have to have such a transverse intersection. So the simple pictorial example is, you know, take a let's just do it in dimension 2. Why do I always go to dimension 3? So take a 2-dimensional, do this where A and B are just bipartite graphs. And so then my condition was saying, well, one of them has no squares. Okay, so the way I programmed it is I have A at this vertex and link B at this vertex. Now, if A has no squares, then when I develop this flat into R2, it can't intersect any vertex which comes from A. Okay, but obviously a flat in R2 has to intersect all the vertices. So, so that can't happen, and then the idea is to try and make that work in higher dimensions. I should also say, or Federico will be unhappy if I don't say, these conditions aren't sharp. There are other things you can do. I mean, obviously there's a lot of choice in what's going on here, right? Because here I said if A is some flag complex and I choose the laziest coloring, then I get the right angle Coxeter group. But if I choose more interesting colorings, I could get out very different groups. And somehow this extra information is where we get some flexibility in creating more functions. Okay, thank you all for listening.
Questions? Okay, so yeah, you titled it hyperbolic groups and their subgroups. It seems in practice you're really taking kernels of maps
Yeah,
Z,
right.
so you're thinking about their normal.
I'm thinking about the normal
Is it,
subgroups.
would there anything be gained from?
So possibly, I guess another thing that I would be really interested in knowing is techniques for showing that a subgroup is finitely presented. If I just give you a group and I give you a subgroup, well, okay, there's a theorem which says that there's a sequence of subgroups of a linear group which are all finitely presented, but you can't decide finite presentation. So it's not immediately obvious that how you're going to say that these things are finitely presented. And one of the key methods that I know of saying that something's finitely presented is Morse theory, or the 1, 2, 3 theorem. But z squared and 1, 2, 3 theorem go hand in hand. So yeah, in practice, we could just look for arbitrary subgroups. In theory, we could just look for arbitrary subgroups. In practice, I wouldn't know how to show that they're type Fn.
You say that this sequence has subgroups. They're all FP, but you can't decide if they're FP. What question can't you decide there? What the finite presentation is for each such subgroup?
Yeah, you can't decide what the finite presentation is. Look at Giles and smile, and he'll explain. But yeah, no, you can't. Yeah, there's no algorithm which will write down a presentation of the subgroup, but you know that they're all finite.
Other question? Yeah.
Are there new properties that one cannot get with right angle Cox that you cannot get?
With these examples, we don't know at this time. We're still searching for interesting examples, and so that's sort of my advertisement. What interesting properties would people like to see in hyperbolic groups, and can we maybe find them?
All right. There are no more questions, then we thank the speaker again.